a joint distribution of the entire thing. Given the joint distribution, I can compute for any Q, I can compute the mutual information. Correct? So these are just numbers for a given Q. And so if I put a given Q, I'll get, so if I just do R1, R2, I get some region, I mean R2 and R1, I get some region for a given PQ, say this is for this P. Now I take a different P, I get a different region like this. And I take a different P, I might get a different region like this. And I take the union of all those things, I get some region like this. That is the region that you want to compute. That is Martin's achievable region. Okay. And the question is really, if I look at this, which is the PUQ that gives me this point? Yes. Exactly. So this kind of, so Q is again kind of a time sharing, but this is slightly something more than time sharing. U is kind of the message that you want to transmit to Y1. V corresponds to the message that you want to transmit to Y2. So it's kind of a superposition coding with some random hashing. That's kind of intuition. So she had this intuition and she wrote what can be achieved, what probability error analysis, and she said that this can be achieved. And I've spoken to her at length, and she said that she doesn't believe, when she came up with the region, she came up from the semi-deterministic setting, and she didn't believe at that time that it is optimal. Okay, she just wrote what she could get. No, I think this thing was really novel here. So how do you, so before this, there was this notion of, there was a region which looked very similar to this, but U and V were independent, conditionally independent, U, V and Q were independent. That's called the Cover-Van der Mullen scheme. And so the question is, how do I transmit correlated information in a way that you can still have some kind of a diagonal structure? And that's why this random hashing came into the picture, to show that that's a large deviation. That's really, it's one of the first uses of the second moment method. Okay, so she had to somehow get the right thing to do. Okay, so it's really very, very nice argument. You go back. Sure. No, I want to see. Sorry. Yes. Yes. No, I just want to see whether this is the best you can, this region is the best you can achieve. Is there, I want to ask, is there another scheme that gives me a point here? This is one particular scheme. So my question I want to ask is there another scheme that somebody can come up with that will achieve a point here or not? I want, yes, capacity region will be the maximum of all the achievable regions. The question you're asking is this the best anybody can do, or can God give me a region that, so anyone say that you can't do it, right? And that's the kind of the question that you want to answer. That whatever scheme you can think of, you cannot get a region. Yes. Yes, this region is convex by time sharing argument. Yes. No, I'm not saying the union of convex set is convex. I said so all I'm saying is that look at the capacity, the rate region. Yes. So there are schemes where the union is not convex, but this case it is. In fact, the Q makes it convex. Okay, the Q makes it convex, and in general, the convexification is not hard. Okay, and the Q makes it convex. Yes, that's the point, and it comes up in certain cases that you have to convexify that. Sometimes the region, the rate region itself is not convex, but then you can actually convexify it. You can get a slightly larger region. No, it's what that. So you will see this in the next setting. You will see this in the next setting. So okay. So now the question is, can we do the same thing we did for the two settings we solved to solve this question, right? Because that's this idea. So we again take the weighted sum rate. So we take the maximum of lambda R1 plus R2. Again, you can take lambda bigger than 1. So it turns out that you can write it in this form. It's lambda minus 1 times something plus R1 plus R2 term. Now this minimum is clearly minimum, or if I just take alpha time between 0 and 1, minimum of alpha ix iq y1 plus iq 1 minus alpha iq y2. It turns out that we can interchange the minimum and maximum. So it's equal to minimum alpha in 0, 1 of this weighted version. And this will turn out to be important for things I'll tell you later. And we can show that, as before, this optimal if and only if this weighted sum rate doubles for every lambda and for every channel. Yes, y1, y2. Or multiple axis. Transmits to multiple receivers. Ideal. It's tensorization, essentially tensorization. It's an infinitely characterization, and that's because you have the Fanon inequality in the end letter, which will give you that. Okay. Yes. So idea is, can I show that this value, this optimal value is, I'm varying alpha and p. Yes, exactly. Yes, I'm trying to solve for the optimizing p. Okay, and that's really, this is the non-convex problem. So, R not equal to 0 means that in this particular setting, I just don't want to make it ugly. There's no common message. So you're looking at a setting where there's no common message. So that's also an interesting setting. You could, because that is a projection. I'm just. No. So, okay. Okay. Yes, I understand your question. So let me clarify. So she said that you pick a P, you can achieve this rate. She has not specified a P. Okay. She says that whatever P you pick, you can achieve this region. And the question to compute the region, so she doesn't tell you a number. She tells you that this is an achievable strategy for any P you choose. And the question is, what is the best P you can choose that maximizes her region, which gives you the extreme points of this region? And I'm saying that in this setting, this becomes a non-convex problem. It's not a it's non-convexity is because if I look at the red thing as a function of P, Q, U, V, the functional is non-convex in the underlying function of P probably. It's kind of, if you just plot it even for simple channels, you'll see something is non-convex. So it's okay, few minutes, but you can verify. Yes. So, okay, you can do the whole thing with just W of y1, y2 given x. Okay, you can do this whole thing given W of y1, y2. But one of the things that's the normal way people present it. But if there's no feedback, the probability of error at this point depends only on y1 given x and only on y2 given x. So no matter how you want to couple the joint distributions, the capacity region is invariant to any coupling. So it's really just a function of marginal loss. It's not a function of joint loss. So if it pleases you, you can make it Markov. If it pleases you to make it as coupled as in a physically degraded version, you actually couple it completely. Okay. So it's up to you how you want to choose this coupling that enables you to compute the region. Right? So, but if there's feedback, yes, you are right that you have to take the joint law. Right? If there's feedback, then it depends. But in this case, I'm assuming no feedback. I'm removing all kinds of, variants of this setting. I'm looking at the vanilla version. Is it clear or no? So the min-max is, so this is slightly non-trivial. It comes from a min-max of Terkelsen back in 70s. There is some kind of convexity which is again powered by the Q, but it's not really convex. So you have some kind of quasi-convex. You have some level sets and some properties of levels. So you use it, but this is true in a lot of settings. The way we prove the min-max, you can use it in a lot of settings, and it turns out So even, okay, I'll come back to this later, a bit later. This step is actually very important because, so okay, I can even tell you here. So if I just stop here, and I ask, is it true that if I put WA1, WA2, WB1, WB2 is equal to sum of these two? That is not true if I stop. That we have a example. So which means that if you want to prove this, you will somehow have to use that they are same components. But whereas all the other proofs, you could use any independent sets and you could have the subadditivity. But the moment I look at this functional, for any fixed alpha, that goes away. So you have something more general that's happening for a fixed alpha. Yes. Receivers? Or two? Oh, more than two receivers, we don't have a candidate region. So you give me a candidate region. We don't have a natural candidate region for more than two receivers. For multiplexes, yes. I mean, we have. Yes. Yes. Exactly. Linear. Yes. 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 Exactly. Yes. I will make at the end of my, towards the end of my talk, what is the general umbrella that covers all of this? What is the things that I observe in this setting? What is my conjectures in this setting, and so on. That'll be the last part of it. Okay. But you see the picture that's coming out, right? So this is the non-convex problem. Okay. Now, in spite of this being non-convex, there's been a lot of. Oh. Yes. 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 And also, so what is nice is, if you want to show a counterexample to optimality, all you need is to construct one channel for which this inequality is a strict inequality, right? So even if you could compute that explicitly, then you have a counterexample, right? So all you need is, and I'll speak a bit more about the setting a bit later, but you will see where it's going. So essentially, this is non-convex, but it has been proven optimal in many settings. So one of the nice results in this whole area is by Curtin and Martin degrade message set. It's a very beautiful result. It touches on various things I'll come to later. It also shown for optimality for class channels by Gallagher. I mean, there's a whole bunch of results, and recently by one Garden, Steinberg, Shamai, and I have done a few works. But the main thing is that you need some new ideas. Okay, so for this broadcast channel, Cover developed the idea of superposition coding strategy. Gallagher developed the idea of how to show subadditivity. That's really how he showed degrade broadcast channels capacity, converse. Then Weingarten, Steinberg, and Shamai, they showed the optimality for a Gaussian broadcast channel setting, where they developed a family of tight convex relaxations to compute a non-convex value. Okay. Now I can relate something to what they did, to what Varun was talking about yesterday. So the underlying functional is something like this. Okay. And here they want to show that this is the optimizer. You cannot directly use a path argument because you could get stuck here. So what they did is, first they did something called channel enhancement, which they created another function which always at least above this, which passes through this point. And now on this function, they did the path argument. That's exactly how they showed this. So and the enhancement was motivated by some KKT conditions on optimality. Okay, so that's the idea of how they did this argument. But to know how to enhance it is normally very, very tricky. You don't know how to enhance it in general. So they could not do it for certain settings, and that's where we developed this alternate way of doing it, and that's where we showed. So I'm going to also mention this technique of establishing extremality without doing a path argument. Okay, that essentially came from the fact that you could not move it to larger settings. Okay, so let's look at the third setting. This is the last of the basic building blocks. So in third setting is the interference channel. So you have two point-to-point communications happening over the same time, except that they are sharing the same medium, so they interfere. So this person wants to communicate to this receiver. The second sender 2 wants to communicate to receiver 2, but since they share the same medium, you get some crosstalk. Now in this setting, you can ask what is the set of all rate regions, rate pairs you can achieve. So Taesun Han and Kinko Kobayashi, this was studied by Australia, but in 81 they showed that you can achieve any R1, R2 that satisfy these 7 constraints. Now, if I don't have this Q, that's coming back to the question you asked me, if I don't have this Q, the union of this is not convex. Okay? But the reason I can put this Q is because there's it's called coded time sharing. You can put this Q in any scheme and you can get something called a coded time sharing, and that makes the whole region convex. Okay, and so that is really the innovation in their paper, because in this idea, there's also very physical significance. What is this physical significance here? So when I have interference channel, what is the normal scheme you can do? Suppose I'm talking to Varun, and Sandeep is talking to Devrat. So maybe Devrat can first either treat whatever I'm talking as interference completely as noise and ignore it, or he can decode part of me, cancel it out, and treat the rest as noise. So the U1 is the part of the first communication that X2 decodes, and U2 is the part of the second communication that X1 decodes, and the rest is noise. That's the basic physical meaning of the scheme. And here you have bounds on U and V, I mean U1 and U2, and you can get this region. This is not exactly the region that they wrote, but the region, it's exactly the same region, but this particular formulation was got by Mehul Motani and Honfa Chong maybe 10 years ago. So that's kind of, it's the same region but a different representation, which is much nice. Again, you can ask, is this the capacity region? This had been opened, we know the answer now, because essentially the problem is non-convex. So, no, so here we have 7 conditions on R1 plus R2. Oh, yeah, you have to do the minimum, right? So this everything is a hyperplane, and you want to take, you should satisfy all of them. Yeah, so in spite of it being non-convex, they have been shown optimality for some classes. And we also know by result of Etkin and Shane Wong that it's close to optimal for Gaussian interference channel. And a lot of nice things came out of this optimality. The concavity of entropy power was discovered by Costa in the process of doing working on the interference channel. There's also a very nice Gini-based approach to prove subadditivity, which is really less explored here, but it's a very nice math tool to prove subadditivity. The way you do it is, suppose you want to prove. So the basic idea is the following. You want to prove subadditivity of some function. You lift it here to a larger space and you project it down, and then you project it back. So it's kind of like a commutative diagram that shows subadditivity here. And this is how they show subadditivity for a certain setting. And so one of the things I'm going to show later is we can show that it's not optimal. That's really by showing non-convexity and showing to how to evaluate this, and we can show that it's not optimal. And the main basic idea is that these settings are far too important to let non-convexity just stand in the way, to not investigate further, and to not investigate classes that require new ideas. So you need to look at some the places where we are stuck, and we need to make some progress. So this is not just my thinking, it's also the thinking of other people. So in particular, so if you look at the book Network Infinite Theory by Gamal and Kim, they have a bunch of open problems, and there are 15 open problems in the first few chapters, and here I'm listing a sub-collection, and you will see why. So this asks the following question, but I'm going to, so this says what is the capacity region of certain setting, all of these kinds of questions like this form, but what I'm going to do is I'm going to rephrase some of them. I'm going to rephrase them the following way. Is superposition coding optimal? Is a particular coding scheme optimal? Is a unconvex scheme optimal? So what am I doing? For every setting, I'm proposing a candidate scheme. I'm asking the decision version, is that scheme the optimal thing or not? And that is the best known scheme for that setting. and the question is that scheme optimal or not. So that means and to test the optimality, you just have to show that whether this S lambda applied for the two tensor is equal to S lambda. That's the same problem. So you want to determine subadditivity of a non-convex function. That's the end of, that's what you want to test. Yes. Yes. No, the equivalent, essentially there's only one side which is hard, which is non-trivial. That non-triviality comes from Fanner's inequality. So it's really simple. So just, it comes, yes. Uh-huh. Okay. Uh-huh. Yes. So let me give you another example, which, I mean, even from setting that I spoke, okay? Let's take the multiplex channel, which means you have two senders transmitting to a common receiver. Okay? There's M1, M2, and they go to a common receiver Y. Okay? You can achieve the following rate: R1 less than IX1Y, and R2 less than IX2Y. Okay? Just mutual information. You can achieve this rate. And you can take the union over of, say, even given Q, you can take the union given Q, and let's call this region R. And you can ask, is this the optimal region? In this case, we know from our study that this is not the optimal region. But if it tensorized, it would be optimal because the n-letter version is the capacity. So the fact that it's not optimal shows that there is some W for which this tensorization fails. And that I can tell you what W it is too, but there are examples for which this tensorization fails. Okay? So the fact that the n-letter becomes capacity is normally very, very simple. It follows from Fanner's inequality. So the heart is really to check whether the tensorization happens, subadditivity happens. Unless you come up with a completely not, scheme, the n-letter will go to capacity just from Fanner's inequality. Yes, because that's why you have this kind of sensorization, right? So I've not looked at because for memory, channels of memory, you may not even have there's no notion, there's no meaning to say that you can look things independently across time, right? So maybe there's a way to compute things, but I don't know of a way to do it yet. Yeah. Is there any more? No. Okay. So now, since we had this idea, we can solve a few things. So we can say that some of them are not optimal. Han, Kobayashi. So we can answer a few things in no, and we can answer a few things in yes. Okay, so, and I think the most interesting questions are the one in blue that's still open. So this is blue that's open, which means that we have a candidate region whose optimality is not known. This is the big blue open question: is Martin's region optimal? This one, 8.4, is Martin region optimal? Is a big open question. Also, there are various other questions where all of these open questions are testing the decision questions. Is a particular scheme open or not? In this setting, so this has been there's been partial progress. So Yuri Polyansky, Yihong Wu, you won't know the optimality for a region, for a candidate region. What they could show, and the region will look like this. What they showed is the optimality of this point and this point. And show the optimality of these 2 points, they actually had to use Wasserstein metric, and they used the relation to functional analysis, measure transportation, and so on. Okay, so these are those. So though they appear, they come from something naive, they relate it to something nice. Okay, we'll see this later also. So that's the setting. So that's basically the first part. So now, So what is the outline for the rest of the talk? So I will show you some aspects of some of the ideas that come in. In the broadcast channel, I'll talk about establishing optimality of some region for vector broadcast channels. Then I'll show how we showed suboptimality of Han-Kobayashi region. And then I'll come to the third part, which is looking at a much more general picture of the family of problems, looking at the sets and what do I believe happens there and what are some of the ideas that happen. Okay. So if I divide the talk into 3 parts, this is the end of part 1. Okay, so that would be you can ask some questions before I go into this. So here you would see part of what Varun talked yesterday of the idea of proving optimality, and I'll talk a bit more about it. Any questions? Or is it okay? Okay, so let's go into the vector Gaussian broadcast channel. This is interesting because it has a lot of relevance, because this is how the multi-antenna systems behave in practice. So you have the same broadcast channel setting. You have a sender who wants to send a common message to the 2 receivers, and a private message to one of them, and another private message to the other person. And you're asking what is the capacity under the setting, except that in this setting, in the Gaussian setting, is a particular channel model where what y1 receives is some matrix A times x plus z, and what y2 receives is some b times x plus z. So it's some linear transformation of x plus some noise. And z denotes, and you can always normalize z to be identity matrix by just rescaling. So z denotes an additive noise, and it models multi-antenna transmitter receivers. It's a downlink problem. It's well studied. And the question you want to ask is whether Martin's region, which he did for any channel, is that the best scheme for this setting? Because now you have a particular channel, you could answer the question, is it optimal for this particular setting, maybe rather in general. So optimality of Martin's scheme was established for the scalar case by Bergmans, and this is, to my knowledge, the first instance where entropy power inequality was used in a event theory setting. And he needed to use entropy power inequality. So this is the first case where entropy power inequality was used. And it was also proof for the reversely degraded setting. It's another setting. And the importance of this setting is Polterev was the first person, to the best of my knowledge, who used this kind of enhancement idea. So he used the enhancement idea to get the reversely degraded setting.